Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the application of IR spectroscopy. And in that we have discussed one of the application, which is the determination of the structure of the compound. So that is the first, and every and each spectroscopy has the first most prominent application is a determination of structure of the organic compound. And in the, as we know that the spectroscopy is known for, the definition we have discussed many times. Let me alter it once again. Electromagnetic radiation with matter is known as a spectroscopy. And whenever IR spectroscopy is discussed or studied, always remember IR correspond to functional group. And as we know that the functional groups, there are different functional groups present in the organic compound. Every and each different functional group has its the position of that particular functional group has a definite position of that particular functional group, and the shape and the size of that functional group remains the same, but sometimes the position of that specific functional group, let's say hydroxy group or the carbonyl group, let's say carbonyl group, the normal value or the position of that functional group is around 1715 per centimeter, that we can call it as the base value of carbonyl group. But if you observe the different spectra, you will observe the shape and the size of that particular functional group, which is very distinct functional group, recognizable functional group, appear, and but the position of that peak sometime is at higher, in some cases, or in some spectra it is lower. And why this so? If such type of the changes observed, it means that there is it involve either inductive effect, resonance effect, hydrogen bonding, or steric effect. And due to these four factors, different four factors, that normal peak position is slightly shifted, sometime at higher position, sometime at lower position. And in the determination of the structure we have discussed, one is a functional group region, second one is a fingerprint region, and third one is a aromatic region. How each and every region is important to provide very characteristic information regarding the functional group that we have discussed with the help of by taking some suitable examples. But right now, at present, what we are going to discuss, let's look at the board. What is written? Application of IR spectroscopy, and we have discussed so far one application which is very important or the prominent, that is a determination of structure. And now second application we are going to study, that is a study of progress of chemical reaction. Study of progress of chemical reactions. So it is another important application of IR spectroscopy. Let me discuss here one example. Let us see either the peak due to hydroxyl group appear around 2500 to 3600 per centimeter, which clearly indicate presence of hydroxyl group. If that peak is broad and strong, it clearly supports the presence of hydroxyl group. Broad peak is generally obtained due to the hydrogen bonding, and as we know that hydrogen bonding, there are two kinds of hydrogen bondings are observed. One is the intermolecular hydrogen bonding and another one is a intramolecular hydrogen bonding. Intermolecular hydrogen bonding means the hydrogen bonding takes place between two atoms, may be same or different. And second one is the intramolecular hydrogen bonding, means the hydrogen bonding occurs within the molecule. So that type of the hydrogen bondings are generally referred as intramolecular hydrogen bonding. How do you distinguish whether the given molecule has intermolecular hydrogen bonding or intramolecular hydrogen bonding? By performing the IR spectroscopy. Observe the spectrum carefully. If you observe the spectrum carefully, what will you see? The broad and the strong peak, which suggests that there is a presence of hydrogen bonding, but we cannot distinguish whether it is due to the intermolecular or the intramolecular hydrogen. Then for the identification, for distinction between inter and the intramolecular hydrogen bonding, there is a very important experiment is carried out. Do you remember that experiment? Which experiment is performed to distinguish between whether the given molecule has intermolecular or intramolecular hydrogen bonding? The name of that experiment, listen carefully. What is it is? It is a dilution method. Dilution means what? The given sample is diluted with the aprotic solvent or the proper solvent. Then again perform the spectra, take the spectra of the diluted sample, and compare these two, or observe the two spectra carefully. What do you observe there? If the peak of initial spectra and the final spectra after the dilution, there is no change in shape, then you can conclude that, or you can say that there is a intramolecular hydrogen bonding is present, because dilution does not affect intramolecular hydrogen bonding. Intramolecular hydrogen bonding does not break by the solvent molecule after the dilution. It remains as it is, means intramolecular hydrogen bonding does not get affected by the dilution. But if there is a intermolecular hydrogen bonding is present, the solvent molecule intervening and the intermolecular hydrogen bonding gets break, and after the dilution the final spectra will appear sharp. It means that the intermolecular hydrogen bonding is broken due to the solvent molecule, and the initial spectra which we have taken without dilution and now is with dilution, totally different. One is a broad and the strong peak. In another spectra after the dilution, it looks as a sharp. It clearly indicates that there is a intermolecular hydrogen bonding is there. So in this way we can easily distinguish intermolecular hydrogen bonding and intramolecular hydrogen bonding by dilution method. Always remember this one. But we are studying a study of progress of chemical reaction. If IR spectroscopy is often used to follow the progress of chemical reaction, to control the chemical reaction, and to study the kinetics of various chemical reactions. And these applications are based on the fact that most chemical reactions involve changes in the functional group. As I already told you that there are a number of functional groups present in the organic compound. Whenever we add the reagent, specific reagent, the whole part of the organic compound is not changed. Only specific part of the organic compound is changed in other. That part is called as a site of reaction, and that site of reaction or that part is called as a functional group. Functional group is nothing as a site of reaction, or in other way around we can define as the atom or group of atom that determine the particular the physical and the chemical property of a particular family of the organic compound is known as a functional group. And this is one of, and this help us to follow up a course of chemical reaction. A sample of the reaction mixture is withdrawn and IR spectrum is recorded. The spectrum is used to determine how far the reaction is progressed and whether it is proceed by expected pathway or not. This can be elaborated with the following examples. Number one example we are going to consider here, this one, you can call it as first oxidation of cyclohexanol, to cyclohexanone. This is a reaction which we already know, and for such a reaction you might be knowing the structure of cyclohexanol. Cyclo indicate as a cycle, see here, hex indicate as a 6-membered ring, and OL indicate that there will be a hydroxyl group. Got it? Now this reaction is an oxidation reaction, and that's why I am showing in the bracket O. And generally here the reagent is used K2Cr2O7 in presence of H2SO4. This reagent is known as a Jones reagent, or the oxidation. The definition of oxidation in terms of the organic chemistry is that the removal of hydrogen atom is termed as oxidation reaction, whereas addition of hydrogen atom is termed as reduction reaction. There are different oxidizing reagent as well as reducing reagent, and from that we can convert one functional group into another, or another functional group into another one. So that way. And finally here, if the reaction is complete, the product will be formed. This is already given, cyclohexanone. This is the product generally obtained over here. This is oxidizing reagent. One of the hydrogen atom from here and one from here is removed, and so this double bond comes over there, and therefore this is a. Now initially we are monitoring this reaction by IR spectroscopy. Initially we took the spectra of cyclohexanol, and cyclohexanol will produce the peak around 2500 to 3600 per centimeter, which is the characteristic of hydroxyl stretching frequency around 2500 to 3600 per centimeter indicate or suggest presence of this is due to OH stretching frequency. Now in between, after some time, the sample is withdrawn from the reaction mixture and IR spectra is recorded. That spectrum shows two peaks, two distinct peaks. One correspond to 2500 to 3600 per centimeter, which we know that the band around this mainly due to the hydroxyl group, and the new band is appear around 1715 per centimeter, which clearly suggests that reaction is going on, reaction is carried out, reaction is taking place, but is not completed and that's why the spectra showing two distinct points, two distinct peaks or two distinct bands, one around 2500 to 3600 per centimeter and second near 1715 per centimeter, suggests that the reaction is incomplete. And now this is a new band appear around 1715 per centimeter, right? Two peaks are there. Again, after some time, again withdrawn the sample and IR spectra is recorded, and that spectra recognizable peak observed produce only one, which is around 1715 per centimeter, and the band which is appear around 2500 to 36 per centimeter, which is absent completely. And this suggests that, this clearly shows that presence of carbonyl group. And so in this way we can monitor the reaction by using IR spectroscopy, whether the reaction is proceeding in an expected way or whether the reaction is completed or whether the reaction is incomplete. That type of the clear-cut idea we are obtained from IR spectroscopy, and therefore this is a second application of IR spectroscopy. Let's see here. Initially only cyclohexanol is present, and the IR spectrum will show OH tracing peak at 3550 per centimeter, and when the reaction is complete, the band at 3550 per centimeter due to OH tracing frequency disappears, and a new band at 1710 per centimeter due to ketonic group carbonyl frequency appears. And if the reaction mixture shows both the peaks, it indicates that reaction is still incomplete. So this is about one of the example we have seen over here. Now let us see another example where we can monitor the reaction, we can study the progress of chemical reaction. Let's see, reduction of nitro group to amino group. Reduction of nitro group to amino group. Reduction of nitro group to amino group. As let us see here an example, suitable example I can say over here. This is a nitrobenzene, as we know that, everybody know that. When it is treated with the reagent, this is a reduction reaction, generally is written as nascent hydrogens, like this. Reduction reaction, here oxygen, here nascent hydrogen, and generally SN in presence of HCl. Tin in presence of hydrochloric acid, which is a well-known reducing reagent. What it will do? It will reduce the nitro group this way into that you are going to get, and this is a structure of nitrobenzene, and you can easily prepare. This is aniline, you know that aniline. which is liquid in nature, reduction of nitro group to amino group. When the reaction is complete, the band at 1540 to 1370, this is due to the nitro group, 1540 to 1370 per centimeter. There are the two peaks due to the nitro group. And when reaction is monitored, sample is withdrawn and the IR spectra is recorded. In that spectrum, if there is a two peak is observed, one which is due to the initial reactant and new band is appear around NH stretching 3300 to 3400 per centimeter due to the NH stretching frequency. When the reaction is complete, the band at 1540 to 1370 per centimeter due to NO2 group disappears. This disappears. And two new bands at 330 to 3500 per centimeter appear due to NH stretching frequency present in the final product. The kinetic study is made by placing the reaction mixture in the spectrometer beam and scanning the desired spectral region at frequent interval. You will get the different type of the signals and the peaks. From that we can easily understood whether the reaction is proceeding in the expected way or whether the reaction is completed or not. So that type of the information we can get by IR spectroscopy, and therefore this is the second application of study of progress of chemical reaction is a important one as the exam point of view is concerned. So these two examples, from these two examples we can clearly understood how we can distinguish, how we can study its chemical kinetics, as well as whether the reaction is completed or still it is incomplete. That kind of the information we are getting from the IR spectroscopy, and therefore this is the second application which is highly important as exam point of view is concerned. So in the next lecture we will discuss about detection of hydrogen bonding, and still then let us stop today here. Thank you. Have a nice day.